Okay, thanks, and hello everyone. First, I think I need to kind of externalize my safety into your hands in a way that, based on past experience of having this sort of stage when giving a presentation has been a kind of hazardous to me. It was a couple of years back when we had a ICES conference. I was giving a presentation in a stage like this, and I get easily carried away when trying to explain something and go waving with my hand somewhere there. And I fell down back there behind the stage. Nothing happened, but if you see that I'm kind of approaching that area or that area, not noticing that what's going to happen, so yell stop or something like this, if I disappear. Yeah. Okay, let's start with the subject. So, Bayesian approach to stock assessment. So I'm kind of going to continue what Carmen started already. This is not a new approach, as you know. It has been used, let's say, at least 15 years. It has been first suggested to be used in fishery stock assessment in the 70s already. And we have been applying developing methods to this direction for quite some time. And there will be two main lines in this talk. I will start by discussing the stock assessment and what I'm here calling, let's say, the burden of statistical data analysis. It seems that we may have had some bad influence on stock assessment from statistics, and I try to somehow explain what I think about that. And that actually is a kind of introduction to the ECOKNOWS project. That's the reasoning behind why we thought that we would need the project that we are now ending. So at the second part, I'm going to try to explain the idea of the project and go in a not into deep detail, but give some ideas about this so-called general population dynamics model that we have been developing as one of the main methods in the project. So let's first say a couple of words about the stock assessment. Many of you have been working with this a lot, but maybe not everyone. So basically, the idea is to concentrate on the future and think about different options. I may decide to decrease the quota or increase the quota of the fishermen, do some other kind of decisions. And basically what we want to know, what is going to happen to the fish stock if I do this, if I do that. We want to explore different options and see what happens. So the main idea is that the focus is on the future. We are not actually that interested about the past of the stock. Of course, quite often we want to look at it and somehow compare it, where we are going to go compared to where we have been, but the main idea is that we want to predict what's going to happen. And of course, to be able to do that, we need to know where we are. So the estimation of the current state of the population is very important. And then on top of that, we need an understanding about the population dynamics. How is this population, or in a bigger picture, how is this ecosystem working and how we are affecting it with our own actions. So we need to have some sort of causal model, maybe some mechanistic description of how things work. Because we are not going to have any observation from the future from which we would learn that what is going to happen. Each time when we are making a decision or stock assessment, we are kind of going into a new area that we haven't seen before. Of course, the idea is that we try to learn from what we have seen already, but that is not going to give us answers readily. We need to somehow try to generalize from what we have seen. And of course, then comparing to the oil spill analysis, I think that's maybe even more extreme, that we really don't want to have that data. We are trying to avoid having any data from oil spills. And as Carmen was pointing out, the estimation of uncertainty is a very important thing, although we heard that we don't yet kind of know what to do with it, but anyway, we are not necessarily using it in the advice as much as we could. But anyway, we are trying to push things into that direction, that we would be estimating the uncertainty that we have, communicating it, and hopefully then taking that into account in whatever management advice we give. But let's first talk about this statistical data analysis that I was referring to earlier. And I now try to here explain a bit what I mean by statistical data analysis. So let's start from looking at this panel here. So we have a set of data, 20 points, which means that we have 40 numbers. And when we think about statistical data analysis, we don't actually care what these units are. We just have some data, and quite often what we want to do is to make copies of this data. We want to somehow, let's say, make a model of this data and try to see that can we somehow condense the information into smaller amount of numbers. So basically try to squeeze this data into a couple of numbers. And one way to do this is to fit a model, let's say a linear regression model to this original data. So basically we have, let's say, about 5 numbers needed to define this relationship if we do linear regression analysis here. So we have gone from, let's say, 40 numbers to 5 numbers, and we have a kind of representation of the original data put into 5 numbers. And based on those 5 numbers, we can then make copies of this data. These are randomly generated from the model that we learned from the original data, so we have made copies of it. And we can see, okay, we basically have, it's not the same data, but it's similar. It looks like the one that we observed already. So the question in most of the statistical data analysis problems is that we want to somehow describe the data that we have observed, make a model out of it, and try to state what we have observed in a more concise manner, have some sort of a kind of a compression of data in a way. And then we have different kinds of statistical tools by which we can then try to evaluate that whether this copying machine, the statistical model that we use, whether it's a good copying machine or not. So we have things like Ecological information criteria, deviance information criteria, Bayesian information criteria, all kinds of criteria to measure that whether we made a good copy of this data here. The blue ones are the original data, and then the gray ones, they are the predicted, the copies that we can make using the statistical model. So we have these information theoretic measures by which we can evaluate that whether we have a good fit with the model, and if we have small number of parameters. The small number of parameters is usually the key in which we want to have, which means good data compression from 40 numbers to 5 numbers. If we had data like this, we might have thousands of numbers and still have 5 numbers in our statistical model fit. So that's, in this context, what I mean as a statistical data analysis. The focus is on data. We want to model what we have seen and make a kind of mathematical representation of what we have observed so far. But how does this compare to the objectives of stock assessment? So in data analysis, as I describe it here, the focus is on observable things. We look at the observations that we had already. We may be interested in generating more of those similar kind of observations, and we want to have a small number of parameters. On the other hand, in the stock assessment, we are not interested about the data itself, typically. We are interested about the status of the stock, and that's something we never ever observe. Maybe the exception is some small salmon populations where we can count each and every one. But anyway, still we want to predict the future, and we don't have any observations from there. So the stock assessment is basically not interested about data, it's interested about something which we didn't see. So we want to make estimates of so-called hidden parameters in the hidden states of the system, which we didn't know. And then if we took this data analysis approach very seriously, and we were thrown some stock assessment data, let's say catches and CPUEs and survey data, we could make a very, very well fitting statistical model, which fits that data and has very good information theoretic properties in making copies of the datasets. And we wouldn't need any concepts of the population size or mortality in those kinds of models. They would be probably just increasing the number of parameters which we don't like in the in the data analysis approaches. So there is the kind of problem that I feel that we may have in stock assessment. So let's take one example of this. Quite often in stock assessment we are considering plots like this, so-called stock recruitment relationship. This is so we have basically estimates of the number of parents in the population and the resulting offspring, how many children those parents had. And as you may know, quite often the plot looks something like this. And maybe the first reaction quite oftentimes is to say, well, we don't have any stock recruitment relationship. And that's of course where you end up if you start with this data analytic approach. You give this to this data a statistician and say that, ask that, would you give us a model that is a good one for this? And that's of course what you get if you do that. So we get a constant recruitment regardless of how many parents we have. And okay, it sounds like a joke, but it's actually used in some of the stock assessment. You know, and the management consequence of this is of course that if you can always take all the parents away from the population, you still have new generation which is about the same size as before. So it becomes an optimization of the size of the fish that which you want to use in, or select in fishing to make it as efficient as possible. But if you then kind of go away from the data analysis principles and start to bring in some biology there, you would maybe say that, well, at least 0 parents should produce 0 offspring, and you may then end up fitting something like this into this cloud of shotgun points here. So now for the biologists it might make a bit more sense to see it like this. But on the other hand, we may have even further information saying that maybe all this data that we have here is from an era of time where we have been actually fishing this population quite a lot. And we may have also information which suggests that maybe this kind of carrying capacity, the asymptote of this plant is not something like 30, it may be something like 70. And if we take that sort of information into account, we might end up having this kind of relationship between these parents and their children, which kind of fits okay also to these points. But the question is that how do you then justify this in the data analytic context? You have been using something else outside of the data to come up with this. And by the way, do you know what people sometimes do to justify that sort of relationship outside the Bayesian inference? Any ideas? Well, we have this kind of art in data analysis, which is to, you know, if your model don't fit, get rid of the data. So remove the outliers. And then it starts to work. Okay, so we are getting closer. And again, not a joke. This is being done as a routine thing in some of the stock assessment, that if your model is not fitting to your data and you have a strong reasons to believe that your model should be okay, you start seeing that, okay, we have these large, big residuals in the fit, so we take away all the observations that lead to these large residuals, and you get happier and you get a nice fit for your model. And you end up maybe in some cases throwing away, let's say, 70% of your data, so you have a couple of data points here left. So we may have a problem there. So how do you know if you have been infected by this kind of data analysis? I have seen this in other people, and also I have had these symptoms too sometimes. So if you see that someone is saying, we didn't have enough data to do this and that, we wanted to have a good biologically realistic model, but we didn't have any data. So that's a kind of sign that maybe we are trying to think in data analysis mode and not kind of like a biological mode in our assessment. Or the data didn't allow more parameters to be estimate it, or someone is reading your stock assessment and says that you are overfitting, you are over-parameterizing this thing, then your reviewer is probably having some small infection from data analysis side. And of course, the kind of big picture is that generally we tend to think that when we have poor data, small amount of data, we should use a simple model. Let's say if you have biomasses of the catches and nothing else, then it's a kind of standard practice to go and choose the very, very simple biomass dynamics model in that case, isn't it? Yeah, that's the usual advice given to you. And if you had this lots of data, lots of surveys, you would have age readings, you have length distributions, you have genetic data, you have spatial knowledge, then you would go and make this more realistic model, the one that you really think that should describe how the population is working. So I think all of these are kind of symptoms of thinking in terms of not as a biological assessment, but thinking in terms of statistical data analysis. And I think this is somehow maybe a bit couldn't say a privilege of fisheries stock assessment, because I think in other fields you take the theory much more seriously. Let's say the climate change. I think those models are mainly driven by the theory and physics instead of statistical data analysis. But on the other hand, I think it's the other extreme where you then don't pay attention to the data that much at all. So I think we are in other extremes of it. We want to, in fisheries assessment, we quite often want to just learn from the data, and if we don't have enough data to estimate, let's say, natural mortality, then our choice is to say, well, we know it if we don't have any data. Makes sense, doesn't it? I'm going to have another example here, and I think this is an example which somehow, at least to my mind, summarizes most of the problems that we have in stock assessment, the typical problem that we have. So let's take a very, very simple problem. Think that we have a population size that we want to estimate. That's of course then uncertain to us if we want to do that. And then we have a capture probability, often we might call it catchability, something which we don't know exactly. So we are going to catch some fish. Let's denote it by X, and of course you might notice that how many fish we expect to catch is the product of the population size and the capture probability. So that's our expected catch. And if we want to somehow make a statistical model for this data that we are going to observe, if we make an assumption of independence between these different captures, we might end up saying that our catch would be binomially distributed, so that we have population size is our number of trials, and then the catchability parameter is the probability for each individual trial. So that's how our model might look like. But you might already see from here that, okay, we are going to have two parameters here and we have only one observation. And now if you have the data analysis symptoms, I think you are going to have some sort of spots that you can't do this. And of course this is how it looks like. If you want to make a simple point estimate, of course the population size would be estimated by the catch divided by the capture probability. But on the other hand, the capture probability can be estimated by dividing the catch by the population size, which we also don't know. So what to do now? So should we stop here? One solution to this problem is, of course, to say that, okay, there is not going to be any quantitative assessments for this stock because we don't have enough data. We would stop there. On the other hand, something which is done quite often, that if we have a parameter which we can't estimate, we start guessing it. And let's say that we have some external knowledge coming from earlier studies, and we have some idea about this catchability. So one simple idea is to assume that we know it exactly. And let's say that our earlier experience says that it should be something like 0.5. And now suddenly this becomes a much easier problem. now we know what the catchability is, we know what the catch is, and we can make estimate of the population size. That's going to be 2,000. So this is of course very similar to the case which we usually have in stock assessment. The natural mortality of fish is something that we don't know exactly, and quite often we believe that we can't estimate it from the data that we have, so the solution is to assume that we know it exactly. We say that natural mortality rate is 0.2, and you have to have very strong reasons to assume anything else in most of the time cases. So this is an analogous to that sort of case. But how about this uncertainty? We want to estimate uncertainty of this population size. Now we have a point estimator for it, and of course now we might ask that is the Bayesian inference, the Bayesian approach going to help us here? And I'd say that it depends. There are many nice textbooks about Bayesian inference around. For example, this is the one that I have used a lot when learning. I think this is familiar to many of you. But of course, regarding the stock assessment, there is this one problem, that it's also concentrated on how do you do data analysis approaches in the Bayesian way. So how do you make models that fit very well to the data that you have done? They are not that much, the methods here, they are not that much concentrating on the kind of the things that we have in stock assessment. How to infer the latent parameters in cases where you have much more latent parameters than your data points are, and where you have lots of theory about how this model should look like. So, nice book, but not necessarily giving everything that we need for stock assessment. So again, going back to the basics of Bayesian inference, Carmen already we're introducing this a bit, but again, just reminding what kind of elements we have here. And maybe the most important thing often to realize is that we have a kind of two different kinds of information in the system here. We have this pink side, which happens in our head. So it's the knowledge that we have, it's different for each person. And then we have the actual real world, the objective world, where we have the data. So the data is thought to be the representation of the real world, and everything else in the Bayesian approach is actually happening in our head. So we are modeling our minds when doing Bayesian inference. And once again, we would start with the initial knowledge. We call it the prior knowledge, and we use prior distributions to describe what we think. Then we have a certain kind of interpretation for this new evidence, and that's often called likelihood. So that's what you make when you try to describe that what kind of observations that you are going to have, what sort of observation model you have. You are basically defining that whenever you observe something, how do you interpret that? So it's also a subjective choice of whoever is doing the modeling. Sometimes people tend to see that somehow this likelihood would be on this objective side, something that comes from data, but of course if you go and look a bit deeper, it's your choice in the same way as the prior. Quite oftentimes it's a bit easier to define the likelihood. You can somehow come to it from let's say making assumptions like independence assumption, which I was doing in this previous example. And this formulating the prior knowledge about parameters, it's much more difficult, but the basic idea is the same. They are coming from our own head. And then the idea is that we use our interpretation, whatever we had in the beginning, we take the new evidence, that's the objective part of the process, and we combine everything. We have a posterior knowledge, the posterior distribution, which is describing what we know. And of course, the idea then is that we use this posterior distribution as the prior for the next case, and then we have a new, potentially new way of interpreting any new evidence that we have. But again, this is the cycle that we think is going to represent how we learn. And what is important here is that we start building these first maybe defining the prior, then defining the observation models, and only after that we go and collect this data. So when we are building the Bayesian models, we should be kind of forgetting all the data that we have and try to build it based on what do we know about the system. So what I'm trying to say that the number of parameters in our model, what kind of complexity we have, shouldn't come from our anticipation that how many observations we are going to have. It should come from the biological understanding of the system and how we are going to measure it. And after that, we should look at the new evidence. So let's see how we would potentially go with this small example here, instead of starting with the point estimate. So the population size is the one that we want to estimate. So in Bayesian inference, we would give a prior probability distribution describing what we think. So this would be the picture of our mind. What do we think about population size? And then we have the catchability here. We may not know that exactly, but you can see that our best guess was 0.5, so it has the highest probability here. Then we have the joint distribution of the population size and catchability here, showing that what do we think about combinations of these two things. And it seems that we basically think that everything is possible based on our understanding at this point. And given all this uncertainty, we can also predict that what sort of catch we are going to have when we go and observe the catch. So that's the basic setup which we have. We have made the model before we have this data. And we actually don't know whether it is the catch that we are going to observe, or maybe we, in some magic way, can also have observation about this population size as well. We may have a new technology coming in and saying that we observe this as well, and the catch, which would be, of course, more informative. So basically, when we formulate the model, we don't know what we are going to observe. If we then go and have the observation, let's say it was 1,000, the situation changes. We are not uncertain about the catch anymore, and we learn a bit about both the population size and the catchability, because we had some understanding about both already, and that helps us to estimate both of them at the same time. Even though we have two parameters, we have one observation. The fact that we had some idea already gives us a small update to both of these. It's not much, of course. We are learning as we go. But maybe the most important thing here is to notice that we have a lot of learning about these combinations. When we look at these marginal distributions, each of the parameters, we didn't learn that much, but we learned a lot about the combinations. So you can see that this weird correlation between these two parameters is describing what we think about the combinations. So first we had this huge space of combinations which we thought is possible. Now we had this one observations, and now we think that, well, they are on this kind of ridge or hill, all the possibilities that we now think. And the reduction of uncertainty is huge in terms of correlation, even though it's quite small in terms of the marginal distributions. So we have learned a lot here. Then just to show some examples, this is something you often, I'm not sure whether it's something you should do, but what people often do is to try to see that, okay, what if I had different mindsets? What if I had different knowledge before obtaining the data? And sometimes the specific case is that, what if I didn't know anything? And quite often, the I don't know anything is represented by completely flat distributions like this. So this is just to show that if you have different kind of prior, you will have a different kind of result. That's the usual thing what's going on, and sometimes this is seen as something we don't want. We are kind of concerned about the sensitivity to priors, which we wouldn't want to see. We somehow quite often want to see that our posterior is always the same, regardless of what sort of prior we have used. Of course, that only means that then we are sensitive to the model that we were assuming, and that's a prior statements and prior knowledge as well. So it is just a different place where our prior information came in, and we are sensitive to a different part of our own judgments. Nevertheless, it might be useful to sometimes try what happens here. And maybe just to make a note that sometimes these flat distributions are marketed as if they would make the analysis now objective, so that you kind of remove yourself from this this exercise. You are not going to affect anything, and only data is speaking. Of course, prior is always a statement of knowledge, and this is a statement of knowledge that you don't have. So it's a question that whether objectivity is the same thing as not knowing anything. If it is, then flat distributions, of course, give you that. But whatever distribution you have, it's always your statement of knowledge. And other persons might have different ones. Again, showing that if we had a bit more information in the beginning, we would have, once again, a slightly different posterior distributions. So that is now describing what we know. Maybe then just adding one more thing into this model is that I made this independence assumption in the beginning, which resulted in as a binomial distribution for these catches. Trying to be more realistic, the independence of fish is hardly ever true in my mind. I think there is always some patchiness, some schooling behavior going on. And I made a small experiment here where I added parameter called group size, which means that our fish would be schooling so that the size of each school would be something like 100 individuals. So I took third parameter to this problem. So now I have 3 parameters and one observation, and I'm still trying to do something here. So if we take into account the group size, I had a prior distribution for it so that the group size would be about 100. My posterior distribution is exactly the same, so I didn't learn anything from this one catch about the size of the groups that we think there is. And the change in this population size and catchability estimate is not that big if we compare. There is some change in population size when we take into account the group size as well. The population size is even more uncertain, but the most uncertainty is here in the correlation between the catchability and the population size, because now we have much wider selection of combinations that can lead to the catches that we have when we have grouping and schooling behavior in this population. And of course, this is the model. If I think that there is schooling behavior, I should have started with this model. So it was a kind of a not that useful play with the independence assumption, which I knew that it can't be true. So this will be my my final model in a way. So what if we took this kind of a data analytic Bayesian approach? So we would go and have the Bayesian approach here, but use this data analytic principles. If we would be slightly infected still by the ideas of data analysis, what would we do? We would probably, in the beginning, already see that, okay, we have one observation, there is maximum of one parameter which we should try to estimate from this, and say that, okay, if we have 2 parameters, it would be overfitting, so we would go and fix, again, the other parameter, and let's say it would be the this capture probability. And of course, you can guess what is coming out of it. We know that we are going to know this population size very, very well if we know exactly what this capture probability is. And you can see from this correlation. Now imagine that you have assumed that capture probability is exactly 0.5. We would only have this slice here as the posterior distribution of the population size. So it's very tightly around number 2000. So we would have, just by saying that we can't, we have uncertainty because we can't estimate all the parameters, we would have made the uncertainty much too small by fixing one of the parameters in order to be able to estimate something based on the data analytic approach. So generally, if we somehow try to compare these ideas, that whether we start from if we forget about the data first and start building the model from the biological knowledge, what is going to happen to the model complexity, and I roughly mean the number of parameters that we have. Or if we start building the model always based on the number of observations that we have, and then try to make a model that we can estimate something from. So if we take it from the biology and we increase the amount of data, now the idea is that we try to have all the complexity that we think there is in the beginning. So we would define all the possible model structures that we think may be relevant for this population. And basically, when we increase the amount of data, it has no consequence on the complexity of the problem. Our uncertainty would decrease, of course, because we start learning that which of these model parameters, which of the model structures are more likely than the others given the data. So uncertainty would go down, but the complexity, the types of models that we have would be roughly the same. On the other hand, if we start like we often tend to do, is that we say that okay, we have a small amount of data, so it means that we need to take this model that has very, very few parameters because we can't estimate many parameters. We would have, let's say, a small biomass dynamic model here, and maybe when we have lots of data, finally we are fitting some sort of a state space model with many migration regions, maybe different genetic subpopulations and so on. But in between, each time we have a bit of new data, we would have kind of expanded our model because now we can estimate a new parameter. And what then happens to the uncertainty here, that it stays in a kind of a comfort zone, something which comes out when you can estimate something. When you can identify some parameters, that usually means that you have about the same uncertainty. Of course, if we kept this complexity the same, so we would use this simple model all the time, then we would see that the uncertainty would go down here as well. But if we start kind of dimension matching the data and the model all the time, we would kind of try to approach what we think should be biologically credible model, one we think should be used. We are approaching that. At the same time, we are keeping the uncertainty about the same. And of course, what is the worrying thing here is that the uncertainty in the beginning here, where we in most cases are, it's much too low compared to the uncertainty that we would actually have if we try to take this complexity and uncertainty coming from our inability to estimate parameters already in the beginning. So that's the dangerous part of this situation. And that's why we wanted to have the ECOKNOWS project. Sakke, by the way, how much time I have?
You have still quite a bit.
How many hours?
How many you need? 10 minutes.
10 minutes, okay. So, of course, there are some things we need to think about when trying to make this change. What if we try to start building the models based on biology and not based on the anticipated number of data points we have? So, of course, we would want to use all the knowledge that we have, because we probably have it from other sources than the data. And again, if we didn't use that, then we would be overestimating our uncertainty if we leave something out. So in principle, we should somehow try to gather everything that we know and try to make realistic representation that we have. So basically it means we need prior knowledge about all the parameters, all the model structures that could be relevant for this problem that we have. And there are many sources for that. We know that they exist. But then, of course, this is because I was kind of saying that we have been using these data analytic approaches. We have had many nice data analytic methods to let's say, decide that how complex model we need. We use, let's say, ECOKNOWS or something like that to see that which of the models give the best fit with least number of parameters. So that's kind of easy. But if we start doing this the other way, we don't have similar kind of tools to say that what is the amount of complexity we need to have. So there is a problem that how do we formulate this knowledge that we have. So maybe we need some model structure, some basic framework where we can do this. And on the other hand, we then need all those prior information put into the model, but then there is the question, how exactly would we do it? We realize that we should and we want to use it, but how to do it? What sort of methods we need to come up with that? And these are basically the questions of ECOKNOWS project, how to try to do all this. And this computation is of course a big question mark here. As Carmen was pointing out that these are already slow, and I think we are noticing that they are already slow. Even we have taken this data analytic approach where we try to somehow dimension fit with the data that we have. And now we are going to say that when we have only one data point or no data points at all, we still may have thousands of parameters. And the problem usually is that when we observe the first data point, it goes huge correlation between all the parameters there, and that is going to give us computational problems. So we have challenges ahead in this area as well. So we wanted to take kind of first steps. I think this is basically what we were trying to say in our project proposal. We were trying to describe the problem that I just showed you, and then say that we need something to replace these ideas, and we need to develop some methods and test them in different case studies, and that's what we have been trying to do. And now, during these 3 days, I think you're going to hear a lot of kind of case studies, a lot of different ways to try to use what we have done, and also see all the problems that we have run into when trying to implement these ideas. So I'm not going to go into deep details of anything. I'm just going to go into this generic framework that we are trying to develop, say something about it, and how it's supposed to work. So the objective for something that we call general population dynamics model, it's a bad name, but it's the first one that we used, and then it's kind of started to live its own life. GPDM. So the objective is that we would have a very flexible model. We can fit it to every fish population. You can think of maybe to other populations as well, maybe to human populations or plant populations. Just the population dynamics of a species. And we would want to see it as somehow easy to tailor, so that we would have a library of model components which everyone can produce, and then they all fit together, and the user in some specific case would just choose, okay, I want this and this kind of function for that, with the, let's say, length of the individual and the natural mortality of it. Different kinds of functions for stock recruitment relationships and so on. And as most of the new methods that we do for this kind of dynamic things is that we want to use a state-space modeling framework. So basically it means that we try to have a model for this hidden dynamics, which has so-called process error. So there is some randomness, something unpredictability in the system, and we use probability distributions to describe how we go from one point of time to the next. And then we also think that we typically can't observe these things directly, so we have a certain kind of statistical models there describing that what kind of observations we are going to have from this hidden process. And we would also like to somehow acknowledge the uncertainty bit we may have about the different model structures. So we may have competing ideas, competing hypotheses about what sort of biological realism or reality we have, and we don't know. We have different representations of them in terms of different model structures, and we would also like to do what is called Bayesian model averaging, calculate the probabilities of these different structures and then take those into account when giving, let's say, the management advice. That's the basic picture how it looks like. It is a bit more messy if we open up these things, but the basic framework is as simple as this. We have the state of the population affecting the state in the next step of time. The step of time may be, in principle, 1 second, it could be 10 years, we don't care. Usually it's 1 year or a couple of months in our case studies. We have some biological parameters here which may depend on the previous state, and these are something which we try to get from our existing knowledge, of course, and that's where we want to have the prior distributions from elsewhere as much as possible. And of course, the generic model that we are building is going to deal with this transition from one state to the next. And in each case, its usage scenario, we then need to think that how will these observations depend on this hidden state. And we try to make a framework where you can specify your own measurements model and take that as part of the bigger model. Maybe just to mention something about this, which might be different compared to other, let's say, similar state space models that are around. We are trying to model the process error based on the assumption that these individuals would be correlated. So it's the idea that we have certain kinds of schools of fish, which we either catch the entire school or almost the entire school, or we miss the entire school, which increases the variance in catches, it increases the variance in survival, and so on. And here is just an example. We end up using so-called beta binomial distribution. If we didn't have any schooling behavior, let's say we are here predicting that how many fish we would, let's say, catch from 100. If we didn't just had the independence, we would predict using the black one. And if we then increase the size of the school, which we believe that there is, we increase the variance, and it becomes quite uncertain if we have a very large schools of fish compared to the total population size. And of course, now this correlation between individuals or the size of the school is something which we again don't know exactly, and we should give a prior distribution for that parameter. So what kind of results we get there? Our objective was to make a very flexible structure, and I think that's something we have achieved. We can do many things with it. We can have many structuring variables, we can include environmental covariates, we can have random effects for most of the things. They can be autocorrelated, we can do model averaging. But is it easy and efficient? Easy to specify, very, very hairy to try to compute anything. It takes a lot of time, and it's not that easy to get the models running. So that's the downside of this development, of course. And you are going to see some ideas how to improve that later on. So, trying to summarize, I think that this lack of statistical identifiability that we have in most cases with our realistic model is something, it's a major source of uncertainty. But we are not going to see that uncertainty if we always choose a model based on whether we can identify or not. So that's something I think we should really think about. And again, Bayesian inference is nice for trying to do this, but of course it helps only if we start building it from this biological knowledge. We took the first steps of this in ECOKNOWS, but as you probably saw already, and you will see in the next couple of days, that we have lots of interesting things to do after this as well. Thank you.